Okay, so let's look at this example of linear regression. We're going to be doing this a couple times throughout the semester. And what we're going to be trying to do is we're going to be trying to fit this curve, which is parabolic in shape. I plotted some data points here. When you plot it, you should use an Excel or some type of graphing instrument in order to put this into your lab reports if you're doing it by my lab class. So you can clearly see here just simply by plugging in each one of the X values, it generates a Y. However, a parabolic shape is a little bit awkward in trying to determine what characteristics this thing has. We know for parabolas that when this value here is greater than 1, it tends to be concave up. But what we want to do is we want to fit this to a line. And up here, I gave you sort of a generic way of looking at the equations based on the lab that you're dealing with. So it's a little bit different from what you see here. So you're going to have to work through this. So basically, I'm taking a second-degree equation, such as this, and I'm kind of writing it in a generic form, where A is this 1/2 g, which corresponds to the acceleration due to gravity. And I'm converting it just to make things a little simpler, look like x squared. You could use t squared if you want as well. And we're going to try and make it look like y equals big A. And I use big A here cautiously, and I made a unique distinction because I didn't want to get confused with lowercase a, which I'm using over here. Again, you can use any letter you want. We tend to stay away from m's in physics because m's, instead of, most of you guys are used to using m's for slope, but we use m for meters, and it could be misconstrued to be mass. So we'll leave that. So essentially, we're taking something that looks like second degree and we're moving it to make it look like something first degree and looks like a line. From that line, we're going to be able to figure out easily what the slope is. So again, here's the graph. That's really not too helpful, but when I convert that equation, make it look like sort of a line, you can clearly see what the slope is. The slope is 3. We can plug in some points here. Now this point over here, sort of an aberration. You can kind of see that it's kind of off the beaten path here. So there may be some issues here in terms of my data. So that's one of the things that you might want to look at. So you might want to, in the calculation, since we typically throw those values out. And I did some calculations based on some points that were on or near my line. So if I were doing some real life data, I would probably throw that point out, use those values that are on or near the line. You can clearly see the slope is equal to 3. Now from this, I'm going to probably want to use this to kind of backpedal and use this information here to gather up some information about this. So that's a clue as to how you might want to solve this. So for you guys are going to probably want to set these two values equal to one another. Remember, this A is the same as this A over here in order to figure out what G is experimental. So hopefully that should kind of get you pointed in the right direction. This is called curve fitting. We change the axes. Instead of y and x, now have y and x squared. And x squared now should have unique units different from whatever x was. Whatever x is over here, if it were seconds, hours, it's now second squared or hour squared, respectively. So make sure that your units are consistent. I just kind of left this generically as just plain old units. Obviously, these units here are gonna be different than these units over here. So make sure you appropriately label those axes. All right. Hopefully that helps you get started. Take care.